Pleasure for me to introduce Professor Abdenacer Makhlouf. He will continue his course on algebraic deformations. Please.
Thank you very much. Let us go with the last lecture of this course. Let me just summarize quickly the last result I mentioned yesterday. We worked out the formal deformations of associative algebra, and I told you that it will work with various algebraic structure. If you have a good cohomology, which fits with these deformations, then we made a connection between the formal deformations. You remember well, we started with an associative algebra where A is a K vector space. And we extended this base field to formal power series and A to formal space, and constructed a family of deformations, which we denoted by mu t equals to mu0 plus t mu1 plus t square mu2, etc. And one of the main results was to see that this mu1 should be a 2 cocycle. And we showed also, maybe a bit quickly, that if you take two elements, mu1 is a 2 cocycle. If you take another element in the same cohomology group as mu1, then you get an equivalent deformation to this one. And then we can state this as a theorem now. Theorem. Not E. Then let mu t be a deformation of A mu0. Then mu t is equivalent to a deformation, is equivalent to, maybe I could remove this word deformation, to, is equivalent to a deformation, which I can write mu t equals to t to power p mu, I need also the first term, mu0 plus t to p mu dash p plus t p plus 1 mu dash p plus 1 plus etc. And here, of course, this mu dash, where mu dash p belongs to Z2, which means it's a 2 cocycle of the algebra A with values in A, and mu dash p does not belong to B2 A. In fact, we notice that only the class of the infinitesimal is important. Then we can always write this, and we have an immediate corollary of this, and very important one. And what is the corollary of this? Corollary. Then what happened if H2 is 0, which means when Z2 equals B2, and if H2 is 0, if the second cohomology group of the algebra is trivial, then all deformations are equivalent to a trivial deformation, are equivalent to a trivial deformation. Okay, this means that your mu t is equivalent to mu 0 viewed as a KT algebra. Then here you can see that we have a criterion showing or telling us that that if we have this H20, then we cannot have any deformation. All the deformations are equivalent to trivial deformations, which means that we cannot deform this algebra. And this type of algebra are called algebraically rigid. We cannot deform them. Huh? Now let me now introduce this concept of rigidity definition. If H2, an algebra A is said rigid, if, sorry, not rigid, but algebraically rigid, because there is other concepts of rigidity, said algebraically rigid, if H2AA is 0, okay? And for talking about other concepts of rigidity, I have to maybe to say a little bit, some words about the structure of algebraic variety of the class of algebra for a given dimension. And now let me just say a few words about this algebraic variety of n-dimensional associative algebra. We can here we can take them unital. Then let n to be the dimension of A. Then if we have finite dimensions for our vector space, we can fix a basis. Let us consider this E1, En to be a basis of A. And if the multiplication on A, which is a bilinear map, A times A in A, this is completely defined if I know it on the basis, because to get the multiplication on any element of A, it's enough to I can use K-linearity and get it using its definition on the basis. Then if I can set this mu Eij on two elements of the basis to be a sum of coefficients, which I denote by Cij k, Ek, and k running from 1 to n. Okay, and here now I can identify my multiplication on A mu with this family of coefficients. This family of coefficients Cijk, where Ijk ran from 1 to n. And this is, you can view it as a vector in K. This is an element in K to n power 3. Okay? And these are called the structure constants of the algebra. Okay, then they have this identification. Now, of course, here in any bilinear map is given by its structure constants, but there is some restrictions which are given by the fact that this multiplication should satisfy associativity condition. And Now let us fix the condition which should be satisfied by the structure constant in order to get an associative multiplication mu. Then this, I need to just to check it again here on elements of the basis. And then what should have mu ei j ek minus mu of ei mu ej ek. This should be 0 for any I, j, k, running from 1 to n. All triples from my basis, okay? Then now I can use the structure constant to define my multiplication. And what I get here it will be something like a sum of C, A, G, not K, but P here, for example, mu P, mu EP EK, and this is a sum over P, minus another sum. I can also use it over P, and this will be mu, this will be, sorry, C, GK, P, mu, EI, EP, equals 0. And finally here, I should have a double sum over P and Q, CIJP, CPKQ, minus EQ, EQ minus CGKP, CIPQ, EQ equals 0. And this vector on A should be 0 if the coefficients are 0. And these coefficients will define polynomials on this CIGK on structure constants. Okay. Then the algebraic variety is defined by an ideal defined by the following polynomials: double sum P from 1 to n, Q from 1 to n, CIG P, CPK Q minus CGK P, CIPQ equals 0. And they should take such polynomials for indices I, G, K, and Q. Oh, sorry, I have to remove here Q. And this is for P. Okay, I have this sum. And for any quadruple IGKQ, having values from 1 to n, I should have this quadratic equation satisfied. And if I have a vector then this as, let's denote it by as indexed by n, this is an algebraic variety. And this is the ideal. This is an algebraic variety. Embedded in K to n, in the affine variety Kn to 3. Okay. And usually the problems we have when we discuss this algebraic variety is to consider components of this algebraic variety, but first, of course, here I have points in Kn power 3, defining each point in this Kn power 3 defines an algebra, but I could have 2 points that define the same algebra or isomorphic algebra. That's why first I need to introduce an action, a GLN action on this. Sorry, it's G like this, group linear action on as N, and it's defined as, if I have here an element F, and on associativity on the algebraic variety as N, I have multiplication. Then to this pair, I associate another element in as N, defined by F inverse, mu composed by mu composed by F tensor F. Okay. Then now I have a fibration, and I could talk about orbits. Huh? Each element in this as N has an orbit. What is the orbit of mu? The orbit of mu is given by all the multiplication, which are belonging to as N, which are associative, of course, such that maybe mu dash here, such that this mu dash is equals F inverse composed with mu composed with F times F, and for F in GLN. Okay. Then now, if H2 is 0, yeah. Now maybe we could also say one word about topology. That usually when you are dealing with algebraic geometry, you use Zariski topology, which defines the closed elements, which are algebraic sets. Then here we use Zariski topology. Zariski topology, and now we can introduce also a new type of rigidity here, geometric rigidity. We say that an algebra is rigid in an algebra A by A mu is rigid, geometrically rigid if the orbit if the orbit is open, is Zariski open. Oops. Okay. And now, what is the connection of this geometric rigidity to algebraic rigidity I mentioned already? In fact, if you have algebraic rigidity, rigidity implies geometric rigidity. And what is the connection between this cohomology and this geometric discussion? In fact, when you have this algebraic variety, here we can have two tangent space to this. If you have a point, if you have mu belonging to as n, then you may have a tangent space to a tangent space to the orbit, and tangent space in the orbit, the tangent space in the orbit, and the tangent space in the variety. In fact, this one corresponds to B2 of AA, and this one corresponds to Z2 of AA. Remember, I told you that we have these expansions, and the first term is the infinitesimal. Now it's exactly what we have. If you have this Taylor expansion, then the first term is exactly the derivation, or the which defines the tangent space. We have this similar result here. Then this tangent space to the orbit, it corresponds to co-boundaries, two co-boundaries, and the tangent space to the variety corresponds to the two cocycles. And when these two tangent space are equal, then this means that we have that the orbit is open. That's why, and if H2 is 0, this means that B2 is the same as Z2, and it implies that they have a geometric rigidity here. Okay, and we can also define another type of rigidity, and maybe if you want an example, because I didn't show any example here. Oops. Well, what about AS2 for n equals 2? Maybe I can take them unital. It is easier here, and you have only two classes. Then it's easy to see that we have, if I take a basis E1, E2, E1, E2, and here E1, E2, E1, E2. If E1 is the unit, then you can fill this one, this part, E1, E2, E2, and what remains is to fill and define the multiplication of E2 by E2. In fact, up to an isomorphism, and if we can see that either I have here E2, you can write E2 here, and 0 here. This is the two orbits I can define on this unitary associative algebra. Okay, then it's here. If you compute the cohomology of this, you can do it as an exercise. Then H2 here is 0. And this means that this algebra is rigid, but this one is not. And it's easy to deform it. And of course, I can just, for example, replace this 0. If I replace this 0 by plus T to E2, then what I get here, it's a deformation of this multiplication. For any T, this new table defines. In fact, I mentioned that we can algebra which of dimension n could be seen as an algebraic variety embedded in K to n power 3. And they are defined by the polynomials I mentioned here. And we define an orbit in order to compare and to identify also 2 points, in this case n to r to 3 n3, which are corresponding to two isomorphic algebra. Now we define this geometric rigidity when the orbit is open. We define this orbit, and when the orbit is open, we say that this algebra is geometrically rigid. And in fact, when we have algebraic rigidity, which means that the H2 is 0, then it implies the geometric rigidity. And the explanation is here. In fact, if we consider a point in as n, and its tangent space corresponds to B2, and its tangent to the variety, to the algebraic variety, corresponds to Z2. And if these two are the same, this means that that your that the algebra, that the orbit is open. Huh? Okay. And here I mentioned an easy example. By considering n equals 2 and considering also the algebra with units. And here we have two isomorphic classes for n equals 2. Then we have either this algebra defined by this table, Kelly table. And in fact, this is C times C. And this is product of K or K times K. And you have this sort of nilpotent algebra because of the zero. This is the other one. But it turns out that for this H2 is 0, and which means that it is rigid. According to our theorem, we cannot deform it. But this one could easily be deformed, and it could be deformed to mu1. We need just to take, for example, to change this E to E2. We define that a new multiplication T, mu2T, by the same table, Cayley table here, and we change E2 to TE2, where T is our usual parameter.
Excuse me, Nasser?
Yes.
In which of the two classes falls the group algebra of Z2? Yeah,
in this one.
Okay. I thought then it would be E2 composes with E2 to EU1.
E2. Of course, here, in fact, here you can put anything. You can put E1 plus B E2. It remains associative.
Okay. Thank you.
And which I've chosen this presentation. Huh?
Okay. Excuse me for interrupting.
No problem. And this one, if T is different from 0, then it is isomorphic to this mu1. Huh? Okay. And one observation I made is that these open orbits help to construct irreducible components of your algebraic variety. Huh? In fact, you have to consider the closure, the Zariski closure of an open orbit, and you get irreducible components. Then, for example, you can have the number of your open orbits, the number of non-isomorphic rigid or rigid algebra gives you the lower bound of the number of reducible components, for example. Huh? Okay. And this one last concept here is the formal rigidity, and formal rigidity is formal rigidity. A is it's when we have formal rigidity when any deformation is equivalent to trivial deformation. And for finite dimensional case, this geometric rigidity and formal rigidity are the same, but we don't have equivalence. We don't have equivalence between algebraic rigidity and formal rigidity, or geometric rigidity for finite dimensional case. We have a counterexample. We don't have any counterexample for associative. For associative algebra in characteristic 0, there is a very, very complicated example constructed by Gerstenhaber and Sheikh, but in characteristic P, but no example, no counterexample in characteristic 0. We don't have I mean, we don't have formal rigid algebra with H2 different from 0. But for Lie algebra, there is an example. For maybe Professor Weigemann will talk about. There is an example in dimension 13, I think, given by Benoit, which shows that we have Lie algebra, which is formally rigid, which cannot be deformed, and its second cohomology group is non-zero. Okay, yeah, okay. Then this is one application, and maybe I should mention here that there is a dual notion of deformation. Dual notion of deformation, and this is called contraction by physicists, or degeneration, or specialization. I mean, you can find all these words. I prefer the second one, but physicists usually use a contraction. What means a degeneration? Degeneration, for example, here, this mu2 is a degeneration of mu1, which means that if you take you take a family, if you take a deformation of this mu2, you fall in the orbit of mu1. Okay, and here degeneration helps to construct reducible components. Then for this associative algebra, unital associative algebra of dimension 2, there is only one reducible component, which is given by this rigid algebra, and this mu2 is in the closure, in the border of the orbit of mu1. Okay. Now let me go ahead with some other properties. This is and it helps, of course, to do some classification and to do geometric classification also of a given algebraic structure. Now let us consider a relationship between Poisson algebra and deformations of commutative algebra. I mentioned this in my introduction. Algebra. We start with okay. Maybe I should define what is a Poisson algebra. A Poisson algebra is given by a vector space, a multiplication and the bracket, where A dot, this is a commutative associative algebra. This is the first condition. The second condition, if I take A with the bracket, then this is a Lie algebra. And the third condition is the compatibility between these two structures. And it's given by the following Leibniz rule. And it shows that this here adjoint is a derivation. And they can write it in this way. Plus, okay, this is Leibniz rule. Leibniz condition. Okay. And now let us see how these deformations are connected, of commutative associative algebra are connected to Poisson algebra. We start with mu A, let A mu 0 be a commutative associative algebra. And now let us consider a deformation, be a deformation of mu0. And you can write mu t mu t of xy, oops. Being mu0 of xy plus t of x t mu1 xy plus t square mu2 xy plus etc. And now we can write down the commutator of this mu t and divide it by t. Then if I take mu t of x y minus mu t of y x, and I divide this by t, what I get here is mu1 of xy, xy minus mu1 of yx plus t sum of mu I of xy minus mu I of yx times t to I minus 1. I'm running from 2 to infinity. Okay. Then if t goes to 0, if t goes to 0, then this term, yes. Then this left-hand side. Sorry. Then mu t x y minus mu t of yx t. This tends to mu1 to what we denote by the bracket x, like this, xy defined by mu1 of xy commutator, mu1 of yx. Then this bracket, now the result here of the theorem here is that that this bracket always define, then if I consider a mu0 and this bracket defined here, and this is Poisson algebra. Okay. Then here we have this is the main result here, and if you have a deformation, a one parameter formal deformation, then the first term of your deformation defined using its commutator a Poisson algebra with respect to the original commutative associative algebra you are deforming. Huh? And this comes from physics, and this t is usually a quantum parameter, like Planck constant, for example. And usually the physicists use h bar for this, and this is called the classical limit, and this is called by physicists the classical limit. Okay. And I don't have time to give you the proof. But now, if you remember, I talked about about quantization as motivation of this. And it is always interesting. Then I told you also that observables in classical mechanics define a Poisson algebra, and then we have a Poisson algebra. If you have take the variety M, then C infinity M with a pointwise multiplication, defined and a bracket. I mentioned that last time. This is a Poisson algebra. If you remember, and one challenging question was to try to construct the deformation of this. And here, this M is called also M is called the Poisson variety, or Poisson manifold. Okay, and one challenging question was to construct deformations of this pointwise multiplication in a way that the first term of this deformation provides, corresponds to this Poisson bracket. Then this is what is called quantization problem. And this is the reverse problem somehow. Yeah, in fact, here we are not constructing a deformation and just picking up this first term and constructing with a Poisson bracket. This is always the case. You have always a Poisson bracket given by the first term by taking this commutator. It's commutator, but here the Poisson bracket is fixed. I mean, we have one more constraint in our deformation problem. And this was solved for a long time, but solved for symplectic manifold. By many people. And the general problem was open until 1997, I think. And it was solved by Kontsevich. Then Kontsevich provides a way using some graphs, etc., to construct deformations of Poisson algebra for any Poisson manifold. Okay. And maybe one more observation, and the time is running. One more observation about associative algebra. It's also about unitarity. In fact, deformation of a unital algebra is unital. Deformation of unital algebra is unital. Is a unital algebra. I mean, this is one observation. One can prove that we can, or if you deform a unital algebra, then you can get a unit in your deformation in general. It is conserved by the unitality is conserved by deformations, by formal deformations. And okay, this works also. This works also for coalgebra. In fact, we can write the same theory for algebra. The same theory for coalgebra, or sort of dual theory. Same theory for coalgebra and bialgebra. And here also we have an interesting result, which says that unit, co-unit, and antipode are conserved by deformations. Okay, and of course this theory could be extended, as I told you, to other algebraic structures. Friedrich Wagner will talk about Lie algebra next week. Then now let me just make some remarks and some comments about other approaches. In fact, this is the most popular way to deform is by using this for one parameter former series. Of course, we can think about considering more than one parameter. This is of course possible, but the problem here is that this ring is not local. This is a local ring, but not the second one. This is local ring, and the second one is not local. And we can also use any instead of this, we can use also any commutative associative algebra as a base for deformation. And then here the particular case of this approach will be the case we discussed already. KT is a commutative associative algebra, and this approach was initiated by Schlessinger, but mainly used by Fialowski and her collaborators. I think Wagner worked on this also. And how this, we call this global deformation. If instead of if you use a commutative associative algebra, and here what will be what you need is an augmentation. Okay, let's call it B. Maybe it's better if B here, and here B is commutative, and what we need here an augmentation. Where M here, where the kernel of this augmentation is the maximal ideal of B. And here the multiplication will be defined as B. We define the deformation on B tensor A. Then multiplication here, multiplication on B tensor A. This will be our deformation. Okay, and of course here the multiplication should satisfy mu A tensor X B tensor X Y. Sorry, this is A B tensor identity mu B. This is my mu B of one tensor. This is a B linear map. Okay, tensor X one tensor Y. And mu associative and epsilon tensor identity of mu B, one tensor X, one tensor Y, should be one tensor mu X, Y, the original multiplication. Okay, Then this is global, these are called global deformations. There are many papers, mainly by Fialowski and other people. This is a sort of generalization, but the main results are exactly similar to the results provided by the Gerstenhaber approach. Now, maybe the last, there is also a functorial point of view to do deformation. Then, in this factorial point of view used by Grothendieck, Laudal, and all these people working in categories, then this functor is called the D def, and it goes from the category of local Artinian K algebra with residual field K into category of sets. Okay. In fact, here also you can find some similar results dealing with cohomology. Huh? Maybe just, if you allow me, just a last comment. And my friend Sergey is here. I would like to say a few words about a topic we developed together a lot. I mean, there is also so-called Q deformations. And these Q deformations works with algebra of vector fields, algebra of vector fields. And algebra of vector fields, and it consists of replacing a Q deformation of an algebra of vector fields, for example, SL2 or Witt algebra or Virasoro algebra. Then it consists on changing your derivation. Then we replace a usual derivation by a sigma derivation. What is a sigma derivation? A sigma derivation is an operator. If you have a commutative associative algebra, a sigma derivation, and then algebra map sigma, then a sigma derivation d sigma on AB. If you have your multiplication, this is d sigma of A, B plus sigma A, d sigma B. Here the dot is the multiplication on your algebra. Then now one interesting example of this is Jackson derivation. And Jackson derivation is defined like this. We deal with polynomials here, and this derivation d with parameter we fix q. This is our quantum element q, and dq of a polynomial p on t. This is pqt minus pt over qt minus t. Okay. Then here with this Jackson derivation, Silvestrov, Hartwig and Larsen, developed a very nice machinery to construct a new type of algebra. In fact, now if you take the commutator, now for example for SL2, if you take SL2, if you take SL2, sorry, pencil is not working. Yeah, SL2. Then usually the basis is denoted by E. Then this could be just D. Derivation H. This is minus 2TD, and F is minus T squared D. And here, if you take sigma, you can take sigma for the sigma of polynomial PT being P of QT. Then this dpq becomes a sigma derivation. Then dq is a sigma derivation. Then usually how to construct this vector field algebra? We take the commutator. And then here, what about the commutator here? Well, what was considered in the literature and also by Sergei and his collaborators was this. There were some examples in the literature, but this was worked out by Silvestrov and the collaborators to motivate some new type of algebra. Maybe you heard a lot already about this algebra called home type algebra. And let me just show you the commutator, how is constructed the commutator in the work. This B D sigma, then this is sigma of A. We have to twist this commutator. D sigma composed with B D sigma minus sigma of B D sigma composed with A D sigma. And this is the twisted commutator with the sigma derivation. And the question now is when you start with, for example, SL2, as I mentioned already, if you take this quantum derivation or this Jackson derivation, then you are taking a quantum deformation of this SL2, and the question whether this commutator defines again a Lie algebra as it is obtained for usual derivation. It turns out that this is not the case, but Jacobi is twisted by the sigma, and Jacobi is twisted. And this type of algebra was called by Silvestrov and his collaborators Homely algebra. And now, of course, the question was how to get pending home-associative algebra. This was our starting collaboration, and we defined home-associative algebra corresponding to this Homely algebra, and of course also other type of all types of algebra could be viewed in this twisted framework, and even more when this wider categories was considered by Canopil. From this category point of view, they also study them from this point of view, and with Panaiti and Menini, we generalized the Menini and Liu. We generalized this Canopil construction, and we introduced more general type of algebra by using two maps. and we call this B-home algebra. And of course, it becomes a little bit more tricky. You have two linear maps, and all the usual identities are twisted. And the challenge was to extend all these classical results to this wider category. We succeed with respect to some result, but there is still lots of questions. Of course, this deformation, this one parameter formal deformation is worked out. We constructed the first term of the cohomology with Sergei, and with one former student, we completed this cohomology, and it works really well for deformations. Thank you very much, and it was a pleasure to give these lectures, and your questions are welcome. If you would like to contact me directly, you are welcome. Thank you.
Thank you, Professor Makhlouf. Indeed, we have not a lot of time for the questions, but for some short question maybe.
I cannot hear. It would be interesting to hear the questions to answer, but the person who is asking question, it's difficult to hear.
I'm not hearing any question for the moment.
Is there any question? Yeah, there is one from Madagascar.
Nicola, your sound is very low.
Okay. Here's my question. Can we interpret the deformation algebra as a perturbation of algebraic structure?
You mean deforming this structure constant? You mean?
No, you said in your last lecture that for deformation we can. I mean, for the definition of a deformation is a series of something. I don't really.
Then it's a formal power series, yes?
Yeah, a power series. So
yes.
Can we interpret it as a perturbation of algebraic structure?
Yes, but yeah, this has been deformation, perturbation. This is just names. We are just moving in somehow these structural constants. Of course, you can say that this is you can call it perturbation if you want. We are deforming the structure, but staying in the same algebraic variety. I mean, the same set of structures. But of course, you can also imagine a deformation. I mean, for example, you can take Lie algebra and deform it in the category of Leibniz algebra. Then it becomes another problem. Huh?
Oh, okay. And in your first lecture, you said that classical mechanics is quantum mechanics is a deformation of classical mechanics. And as we know, classical mechanics is represented by the Poisson algebra, and quantum mechanics is using Heisenberg group, like it's a Lie algebra. And can you think that Poisson algebra is Lie algebra is a kind of deformation of Poisson algebra?
In fact, I said that you have this classical mechanic, which is given by this Poisson algebra, and in quantum mechanics you have this bracket. I mentioned this bracket is a deformation of the pointwise multiplication, and it's also constructed with respect to the Poisson structure.
Okay.
It is in this sense. I mean, it's one approach. I mean, I don't know if all the physicists agree with this, but it was done mainly by mathematicians. This quantization deformation.
Yeah, thank you very much. Your lecture was very interesting.
Yeah, thank you.
Yeah.
Thank you. And
another question. So, thank you for the good talk. And I ask you if the sigma derivation is a particular case of generalized derivation of Lichy and Lux article.
I think it's a little bit different because what we call generalized derivation, there's many types. Sometimes we use several operators so far. I don't think that it's exactly what is in the paper by Léger and Lux.
Mm-hmm.
It's a generalized derivations for sure, but,
yes.
but it's a different type, I think.
Okay. I will thank you for the good talk. It's a great talk, and it's very clear. We have a new notion of deformation and algebra. As we know, Madagascar haven't this topic in the course of master or PhD study. So thank you very much for this new notion. Thank you.
It's a pleasure. Thank you very much for the invitation too.
Hoping to see you on another occasion.
Hope so.
Okay.
I'd be happy to visit. Unfortunately, I plan to come, but I think many people were happy to visit you, but unfortunately, the situation is not allow us.